Chapter 15 homeworks. Does anybody have any questions or things that we need to address before we get started on kind of where we left off and kind of things moving forward? Victoria? Sure. Let's take a look at those. All right. Does anybody have a preference, 83 through 92, that they'd like to see done? If not, I can just do it. Not a big deal. Okay. So for all of these problems, we're going to be using the product property, the quotient property, or the power property, or multiples, many of these. You could use all three of them or whatever, possibly. So for example, if we're doing 83, I notice that I see the plus sign, so I could use the product property there, just to write that as log of xy. Or if I was looking at, say, 89, I notice that I have a power property in the coefficients. So that would turn this into natural log of x squared plus natural log of y cubed. But then I also have a product property there. So I could put them together. Does that ring some bells there, Victoria, on what to do with that? By and large, that's what you're doing on all of these, is just using product quotient or power properties or some combination of them. You could use all three of them potentially in a problem. Feel cool? Okay. Others? Questions from this homework? Okie dokie. We'll just kind of get started then with our things here, and we can always circle back and come back to this stuff as we go. So let's do a brief review here, because it's some we basically had half of this chapter was done before break, and now we're going to finish this chapter after break. There's probably some stuff faded on us over spring break. I don't imagine all of us were sitting around studying our math and doing homework over break. Maybe some of us did a little, probably not a lot, which is okay. Relax, have a break. That's what it's there for. All right, so in this chapter, what we have done so far is we've talked about three types of functions. We've talked about exponential functions, logistic functions, and logarithmic functions. The key piece that we had been working on before we left for break was this relationship between exponential and logarithmic functions. So for an exponential equation like b to the x is equal to y, we know that the b value, when we define an exponential function, had to be a positive number and cannot equal 1. Now, if this value for b is positive, what can we say about y? If I take a positive number and raise it to a power, What kind of number do I have to get back? A positive number, right? There's no way that raising a positive number to a power can give me 0, and it can't give me a negative. So I know also then that the y in this case would be a positive. Everybody's okay with that? Okay. So what we can do, or what we did in the previous chapter, is that we defined this new function, a logarithmic function, which is basically the inverse of an exponential function. So this is this exponential equation, b to the x is equal to y, is the same as the equation log base b of y is equal to x. And because these two equations are essentially the same thing, just kind of rearranged, we can say the same requirements as to the value for b in a logarithm and the value for y in this logarithm or logarithmic equation. The important takeaway here was that the y has to be positive. We cannot take the logarithm of a negative number. We cannot take the logarithm of 0. Those things are undefined. So that's important finer point to make sure that we kind of reiterate. Okay, so we can take the logarithm of positive numbers only. No negatives, no zeros. Everybody's cool? So let's think about this a little more. What this logarithm is answering is basically what is the exponent that does this. So for example, if I say, okay, 2 to what power gives me 3, well, that power should be log base 2 of 3, whatever that number is. That's just the name we're going to give that number. Everybody's okay with that idea? Okay. Now there were a couple of important observations that we made about logarithms. So the first observation was that the logarithm of 1, any logarithm of 1, it doesn't matter if it's log base 2 or 10 or e or 17/3, it's always 0. And the reason is that we know that any non-zero number to the 0 power is equal to 1. Right? That was a property of exponents that we would have talked about in our Algebra 2 class. 0 to the 0 is undefined. It's actually indeterminate. That means that, like, depending on kind of how you thought about the question, you get multiple answers, which is not what we want. We want deterministic math where, like, 0 to the 0 is always the same thing. If it has multiple answers, then it's undefined. We don't like that. Right? We don't want 2 plus 2 to be 5 sometimes and 4 some other times. That's not how we want, not how math works for us. Is that okay? The next one was that log base b of b is equal to 1. This is basically just saying that b to the first is equal to b. Of course, right? But, you know, so log base 10 of 10 is 1. Log base 7 of 7 is 1. Log base whatever of whatever is just 1. The next piece was that log base b of b to the y is equal to y. So what we're kind of seeing here is that log base b is kind of canceling out that exponent base b. giving us y. The reason there is if we build the exponential equation out of that, we just have that b to the y is equal to b to the y, which no doy. And then the last piece was if we take the exponential equation, b to the log base b of x, that's equal to x. So if we take that exponential equation, write it as a logarithmic equation, we have the exponent is equal to log base b of the answer, which of course log base b of x should equal log base b of x. Like that's, you know, like one of the fundamental rules of mathematics is that a number is equal to itself. These two results here are going to be the hyper important ones for what we're going to do today. So what we're seeing is to cancel out, or in the first one, what we're seeing is to cancel out an exponent base, we use a logarithm. And in this one, we're seeing to cancel out a logarithm, we use an exponent base. That'll be super important going on with what we do today when we talk about solving. So those two observations that we made last week will be super important here today. Or not last week, but like the week before we left for break. Maybe we didn't even do it that week. Maybe we did it the week before. Shoot, I don't remember when we did it. Just say previous. You know? And then the last thing that we had done before we left for break was talk about those three properties that I mentioned at the beginning of class when Victoria asked about homework's 83 to whatever. I don't remember what that went up to, 89 or something. 92, I don't remember. But those three, again, were the product property, the quotient property, and the power property. So everything that we've just talked about here is kind of the key pieces that we had mentioned before break for what we're going to be doing today. So I just wanted to make sure that we had kind of gone back and revisited these things just to kind of get us prompted and warmed up for diving into section 15.4, which is what we'll be doing today. Or some of what we will do. It'll take 2 days to do this section. Because I'm going to do the fundamentals in the first half and then the applications in the second piece. Okie doke. All right. So 15.4 is all about solving. So there is kind of two different approaches we can take to solving. I want to say, like, although they're both really doing the same thing, but like depending on how you want to think about the problem, you can do it either way. It's doing the same thing. So one approach is just taking advantage of this one-to-one property. So for an exponential equation, if I can write that exponential equation so that both the left-hand side and the right-hand side of the equation have the same base, then I can just set the exponents equal to each other and solve that. Now, sometimes it's tricky to get the left-hand side and the right-hand side to have the same base, but if I can do that, I can just set the exponents equal to each other. And then I can say the same thing about a logarithmic equation. That if I can rewrite my logarithmic equation so that the left-hand side and the right-hand side are both log of the same base, then I can just take the inside parts and set them equal to each other and solve. And this feels very common sensey, right? Clearly, if I have 2 to the third is equal to 2 to the x, then x has to equal 3. Right? If I have something like this, that should be really obvious to see that we could say that. Similarly, if we have the natural log of x equals the natural log of 2, well, again, clearly x has to just be 2. That's kind of what these one-to-one properties are saying. The tricky part is getting your equation into that form where you can do that kind of thing. So we'll talk about do some examples and how to do that. And then we'll talk about an alternative approach that we can take that I think is a little more systematic and often an easier approach for students, but less intuitive than this is. It's okay? All right, so let's say we have 12 times 3 over 2 to the x over 5 is equal to 27. So intuitively, what would be the first thing you guys would want to do here? Any answer is fine. In fact, even if it's wrong answers, that's good because it gives me an idea of what your initial intuition is. And we can talk about why we could or couldn't do that or why it might be a good idea or bad idea. Because what your initial idea is here would be the same thing you do in the test unless we make a correction, right? Unless I tell you, oh, yeah, you don't want to do that because da-da-da-da-da, and then you can update how you're thinking about things. But even if you're telling me the wrong thing to do, here, that's an effective, teaching moment. And it's better to do that now than it is to sit on it until a test or whatever, right? You guys see what I'm saying? Claire, what's your thought there? I saw you mouthing something.
Maybe get rid of fraction.
The 3 over 2? How are you going to do that? What's up?
This says x over 5.
Yes, in the exponent. Okay. Okay, so you would want to get rid of that fraction in the exponent. So remember here when we're solving, so normally when we simplify, we go kind of that direction through the order of operations, right? When we're solving, we're going to go that direction through the order of operations. So the exponent's pretty far down the line of what we want to take care of. So I'm not sure I'd want to do that initially. Does that explanation feel good as to okay, I can see why I would want to wait on that. Eventually, yes, we do have to take care of that, but I would not worry about that for a while. What else? What other ideas might you have? Again, any idea is fine. Like, just say something, and it allows me to like, okay, like, that's a bad idea, and here's why, or that's a good idea, and here's why. Claire?
Divide the 27.
Okay, so I would go the other way. I'd divide the 27 by 12. Yes, yeah. So, great. So if what we're trying to do is get like b to the x equal b to the y, I got to get that thing out of there, right? So dividing both sides by 12 is a great first step. What would worth mentioning here, is it okay to multiply the 3 over 2 to the 12? Can I just multiply those two numbers together? No, why not? Yeah, very good. So remember, the way that we multiply things together is if I have two numbers and I multiply them together and they have the same exponent, I can multiply the bases together and keep the exponent. Or if I have two numbers with the same base but different exponents, I can keep the base the same and add the exponents. But if I have something like this, where the bases are different and the exponents are different, there's nothing you can do. Again, these are kind of exponent rules, basic multiplication rules, but it's worth like just recapping that. 27 divided by 12, I can reduce that to 9 over 4. I know some of us are very anti-fraction, would love to make that a decimal. I recommend not doing that here. If we're going to try to rewrite these with the same bases, you're going to get yourself into a lot of trouble doing that. So again, as tempting as it is to like, oh yeah, I'll just write that as a decimal instead of a fraction, you're going to miss the necessary steps here by doing that. Everybody okay with what we've done so far? I've kind of been tangenting off on like other hypothetical things that we could or couldn't do, but I think that's often effective in just kind of helping us kind of sort our way through this. Okay. So the left-hand side looks good, right? I have just some base to some power. I have a b to the x over there. Everybody kind of see that? The right-hand side now, what I need is I need to rewrite 9 over 4 so that it's a power of 3 over 2. Does anybody see a relationship between 3 over 2 and 9 over 4? How about a relationship between 3 and 9? How about 2 and 4? What if you're thinking about an operation other than multiplication? So 3 and 9, and then 2 and 4. Squared, right? 9 is 3 squared. 4 is 2 squared. Everybody agree with that? So 9 over 4 is the same thing as 3 over 2 squared. We see that now. Now, the bases of our exponent are the same. Everybody can see that? So according to that property that we stated before, I can then just take the exponents and set them equal to each other. So to solve for x, what I need to finish by doing is multiply both sides by 5. Yeah. Now, what's typically the most problematic step is doing this kind of thing, right? Is noticing that I can rewrite 3 over 2, or 9 over 4 as 3 over 2 squared, right? Sometimes this is, in fact, this is a fairly easy observation to make in compared to some problems. So Mr. Kulik, what if I just am like, I don't think I'm ever going to be able to see that? Is there another thing I could do to solve this problem? Or another way of thinking about solving this problem, if I did not feel confident that I could do that. What do you guys think, considering I'm making a big deal of this? Yes, yeah, there's another approach that you can take that's a little bit more systematic. So let's go back and point out this green box here. Specifically, this first property. So what we're observing in that property is that, well, actually, let's just say this part, is that a log base b is canceling the exponent base b, leaving just the exponent y, right? The takeaway here is that I can use a logarithm to cancel off the base of an exponent. That's what I'm going to be doing as an alternative way to solve once I've gotten to this point. So I want to cancel off that exponent base of 3 over 2. To do that, I'm going to use a logarithm. Which logarithm do I need to use? I need the base of my logarithm to match the base of my exponential. So in this case, I should use log base 3 over 2. Everybody's okay with that reasoning? Now I want to be clear here. There's no reason we have to use log base 3 over 2, but it makes the arithmetic massively more convenient to use that so that the base of your logarithm matches the base of your exponential. But really any log is going to be okay here, but it makes it, if you did like log base 10 or something, it's just a little bit more of a hassle. Just to be clear. Everybody's okay still? All right. So that's going to cancel. Log base 3 over 2 is going to cancel exponent base 3 over 2. And then we would proceed just like we did before and multiply both sides by 5. So I'd have 5 times log base 3 over 2 of 9 over 4. And now it's just calculator time. Remember how to type in a logarithm of the base of your choice is you press the math button and you scroll all the way down till you find the log base command. And that allows you to type in whatever base you want for your logarithm. And it's 10. Same thing that we got before, right? Is either method okay? Yes. Well, Mr. Kulik required you to do one way versus the other. No. The advantage of this second way I've shown you is it scales very nicely. Sometimes, like, how the heck do I rewrite this number as so that it has the same base as the other side is a kind of a particularly difficult question. It's never going to be any more difficult than what we did here. So the second method scales very nicely because it's like always the same process. Which is nice, right? That's what we prefer, is to have everything always be the same. So it's not like any tricky thing going on. Let's do another example. Yeah? Okay. So we have 14 times 1/3 to the x minus 1 equals 126. First thing we should do is excellent. Divide both sides by 14. Get that out of there. Regardless of which method you're going to use, that needs to be the first step. And then I'm going to write this twice, where we're going to do, one way and then the other way, just so you can kind of, again, see in real time what the difference would look like. So our goal here now is going to be to rewrite 9 as a power of 1/3. Now that's a little bit more difficult question than the previous one, although I can see a relationship between 9 and 3, right? What's the relationship between 9 and 3? Squared again, right? So I know that. Now here's the sneaky part. You remember this property from last year, property of exponents, that a negative exponent makes a reciprocal? So I'm going to use that here. So if I make a reciprocal, I'd also need to make a negative exponent, right? Because if I make the reciprocal and give it a negative exponent, it's like I've done nothing at all. Now that's pretty sneaky, but we've accomplished what we needed. Everybody's okay? Sneaky though, right, Mr. Kulik? Alternatively, if I approach this thinking I'm just going to cancel the exponent base of 1/3, what would I do to both sides? Log base 1/3 to both sides, yeah. So those cancel out. Oops, that was x minus 1. Just copied it wrong. So far, so good. And then we just add 1 over. And it's calculator time. So 1 plus, and then to get the log base 1/3, I press math and go to the log base. And I get the same answer that I did on the other side, or with the other method. You'll notice that essentially we did the same amount of work, same number of steps. Either way of method is fine. I think the second method is more systematic because it's like you never have to do anything clever to get it to work. It's just like just got to use a log, any log. Now the best log is so the exponent base matches the log base. But like I could do any log I want and still have it work. It's more of a hassle. But and even remembering that exponent base needs to match the log base, that's easy to remember even. You know, it's not like the other thing. It's like, oh, I have to pull out some weird property of exponents I haven't thought about in a while to like switch things around to make it work. But they both methods are appropriate. Do we feel okay on that sort of a situation here? Okay. Let's look at a trickier version of this kind of problem. So let's say we have 3 to the x plus 3 to the negative x equals 2. Yeah, of course. So you look at this, and there's a bunch of things in here that should be like, oh, boy, Z, that's kind of a problem. So right away, what kind of things do you see that are like, this is an issue? What'd you see?
The negative x.
So we have a negative in the exponent. Yup, very good. What else? I see x in more than one place, right? I have a 3 to the x and a 3 to the negative x. Oh, boy, Z. And then I also have this fraction floating around in here, right? That I have this thing over 4. So those are probably the 3 things that are just like, I'm not sure what to do with this. Any ideas on the first step? What the first step might be, or a reasonable first step? Ben?
Multiply by 4.
Yeah, let's get rid of the fraction piece at least. That should be an easy first step. Will make our lives a little bit easier because it's often more convenient to not have to deal with a fraction. Okay, everybody feel okay with that? All right, now what? Can I add 3 to the x and 3 to the negative x? No, man, they're not like terms. Why not? One of them it's x and the other it's negative x, right? Landon? So here's the problem with doing that, trying to do that now, is that logarithms, you can't use term by term. You can do it to the entire side, but log of 3x plus 3 to the negative x, I can't cancel the individual exponent bases. I need to get that to a single exponent base in order to do that. Does that make sense? So everybody else, what we're saying is that like log of a plus b is not log of a plus log of b. So I can't just log each of the 3 things and be done with it, which is unfortunate. Victoria. Well, if I was multiplying the 2 things together, I could do that, yes. Here they're being added, right? Like 2 squared plus 2 squared isn't 2 to the 4th, right? It's just like 8. So here's the trick. I'm going to multiply both sides of this equation by 3 to the x. So that would distribute through here. So I'd have 3 to the x times 3 to the x plus 3 to the x times 3 to the negative x equals 8 times 3 to the x. So 3 to the x times 3 to the x, we can add the exponents and get 3 to the 2x. 3 to the x times 3 to the negative x, we can add the exponents and get 3 to the 0. But I can't multiply 8 and 3 to the x, so that's all going to stay the same. Everybody okay with what I've done so far? Okay, what's 3 to the 0 again? 1. Very good. So I'm going to move everything onto one side. And hopefully, if I prompt you and ask you the right question here, this is going to remind you of something else. What kind of an equation have we solved before that has like 3 things like added or subtracted from each other? We would have solved them all the time last year. You had 3 things that were like added or subtracted from each other. There's no wrong guesses here, guys. I mean, there's wrong answers, sure, but like it's fine to be wrong. Great, a polynomial. Specifically, what kind of polynomial? Starts with a Q. Quadratic polynomial. It turns out that if I think about this in the right way, this is in the quadratic form. So, if you remember this property of exponents, that the exponent of an exponent, we multiply exponents. You guys remember that property? That look familiar? If I apply that here, I can, instead of thinking about that as 3 to the 2x, I can think about it as 3 to the x squared. Is everybody okay with that? And now if I just say, let's just make those 3 to the x's y's for the time being. So it's like a little bit more clearly quadratic. What I have is a quadratic equation, right? Now we should be able to see it quite clearly. Yeah? How did we solve quadratics last year? What were some of the methods we used to do that? Quadratic formula. The other major method we would have used was factoring, right? Now, to factor this, I would check factoring first since the leading coefficient is 1. To factor this, we'd have to find 2 things that multiply to give us 1 and then add to give us -8. I don't know of 2 integers that do that. Everybody agree? So this one will not factor nicely for us. So we should, in fact, use the quadratic formula as Jay suggested. So the quadratic formula, yeah, of course. Is this. If you don't have that written down or memorized yet, I would definitely write that down here because you will use that in your homework. So in our case, A is 1, B is -8, and C is 1. So everybody okay so far? I'm trying to be like super clear about what it is that I'm doing because, well, we've been at it for a minute here. So negative 8 squared is 64, minus 4 is 60. And 60 is what? 4 times 15, right? Why was that be important? Because the square root of 60 is also equal to the square root of 4 times the square root of 15. And the square root of 4 is just 2. So that can reduce down to be 4 plus or minus square root 15. So far, so good. But we're not solving for y. We want to solve for x. Remember that we said x was equal to 3, or was, I'm sorry, y was equal to 3 to the x. So far, so good. Everybody's okay with me breaking that plus or minus into 2 separate equations like that? Since we're going to have to keep on solving, it's a good idea to do that now. So what do I need to do to solve for x now? I have 3 to the x equals 4 plus square root 15. What do I need to do to get the x by itself? What? A log, yes. Which logarithm? Log base 3. And obviously we would do the same thing over here, right? Yeah. So I get 188-ish. And here I get negative 188-ish. Am I guaranteed for that always to work? No. Why? What could go wrong? Remember, when we take the log of something, we can only do that to positive numbers. If the answer to that quadratic was 0 or a negative, those things would give you an error when you tried to take the log of it in your calculator. That part is just going to give you no solution from it. So you could get, if you remember when you solve a quadratic, you might get one answer that's positive, one answer that's negative. In that case, one of those would give you an answer when you solve the exponential, and one would not. And that's okay. The one that doesn't, just there's no answer for that part. Does that make sense, guys? Okay. All right. What if we have a logarithmic equation now? So again, we're trying to solve for x. What's the first thing you think we should do here? Excellent. Yes, let's get rid of that multiplication going on, right? We have this times 3 that's going on outside the logarithm. So we have that. Now we can either try to rewrite the number 2 as the log of some number, not my preference, or we can try to cancel out this logarithm. So if I go back and to that green box we had made, we're going to now be using this piece, which says that I can cancel logarithm using an exponent base. What exponent base do I want to use to make this as easy as possible? The base that matches the logarithm base. So if I go back to my problem we're working on, what is the base for the logarithm here? What? Yes, very good. How did you know 10? Because it doesn't have a number there. So if we just write log, we understand that to be log base 10. That was the common logarithm. So I'm going to do the exponent base 10 to both sides, and I'm going to write it like exaggeratedly big, because I want to really emphasize to you that we're not multiplying both sides by 10, that 10 is the base of an exponential. So go ahead and write that 10 as big as you possibly want. Really encourage yourself that we're not multiplying here. So I get x is equal to plus or minus 10. Everybody okay? Hold on, though, because we're not done. Remember, can we take the logarithm of any number we want? No. Has to be positive. So every logarithmic equation you solve, you need to check to make sure that the solution actually is possible. So if I go back, I'm going to look at taking my 10. If I plug 10 in for x, and I take the log of that, does it work? Yeah, 10 squared is a positive number. So that's good. That one works. If I take negative 10 and I go and I plug that in, does that work? Yes. So those are my solutions. Okay, so far so good. One more example, we'll be done for the day. Sound good? Ben? Yes, sir. What letter are we on now? Is it E? Sure. All right. Oh, Boise. I look at this one, and there's some weird stuff going on here. What do you notice? I got x's in 3 places, and I have 3 logarithms, right? What does ln mean again? It's log base e. Remember that irrational number e that we talked about in the before break? All right. So the first thing I want to do is I want to condense this down so that I have like a single logarithm on both sides. So on the left-hand side, I have to somehow get rid of the addition. And on the right-hand side, I have to get rid of this times 2. How am I going to get rid of the addition on the left-hand side? We're going to be using the product property. So no. Remember what the product property says? It says log of xy equals log of x plus log of y. So I can do that. Everybody's okay with what I did there? How about on the right-hand side? How am I going to get rid? What am I going to do with that times 2 out there? Great. I'm going to use the power property that says log of x to the c is equal to c times log of x. Oops. Everybody feel okay there? So we can use that one-to-one property now and just, we can drop the natural logs since we have a natural log on each side. A single natural log on each side. Everybody's okay with that? We're using that one-to-one property we mentioned in the beginning, or you could think about doing exponent base e to both sides. Either is thinking about it as the same. So when I FOIL this out here, I just FOILed that in my head quickly. That's okay. What kind of equation do I have here? Quadratic. To solve a quadratic, the first thing I should do is, now I do something before I do that. To solve a quadratic equation, it must equal 0. So let's subtract x squared from both sides. Then we could either try to factor this, or we could use the quadratic formula. Since the leading coefficient is not 1 in this case, I know to factor it, it's going to be that long factoring that's kind of a hassle and isn't even guaranteed to work. So I would just go straight to the quadratic formula here. Let's see, 25 minus 16 is 9. The square root of 9 is 3. So 8 plus 3 over 4 is 2. And 5 minus 3 over 4 is 1/2. Are we done? No! What do we still have to do? We have to check. So if I take 2 and I go back to the very beginning, if I plug 2 in, 3 times 2 minus 2 is positive. 2 minus 1, positive. 2, positive. That one works. Let's try the 1/2. Oops. 3 times 1/2 minus 2, negative. I don't care what happens after that. As soon as I get one of them that doesn't work, I'm going to toss it out. That is extraneous. So I just get the one solution, 2. Keep in mind when you're checking like this, both answers could work, one answer could work, 2 answers could work, no answers could work. It's all possible. Okay, it doesn't mean that you've done anything wrong. All right, we'll stop here. At this point, you guys should be able to do up to 130. There's 180 problems in this problem set. I know.
They just keep going.
They just keep going. We have another half of this section still to handle, and then a whole nother section after that. So, dude is right. Well, we're stopping here today because that felt like enough.